Hey guys, back again. This week we're going to be covering chapters 3 and chapters 4 in the text on landforms, weather, and climate. And finishing up with those two chapters, that's going to set us up for what we're going to be covering in the first exam. So I want to kind of just give you a brief overview of both of those chapters. I'll come back with a second video for the weather and climate piece. And here we're going to cover some of the stuff that's going on in chapter 3 and what is happening with landforms and what geographers are looking for in landforms and what's known as geomorphology. So we're going to go ahead and get into that here, and hopefully I can actually get this to work. There we go. And just going to maximize that. And so here we can see it. We have our chapter 3. So what are we going to be covering? Just the basics of Earth materials, a little bit about geologic time, tectonic movement, a little bit about what are the tectonic forces that are going on, gradational processes, and then if we get back into what we were talking about in chapters 1, a little bit, and a little bit in chapter 2, but landform regions. So how can we actually use landscape features to define landforms and what's going on with that? So when we're talking about landscapes, we're generally going to be talking about geomorphology. Okay, so geo, again, the earth or the shape of the earth, and morphology. So to morph, if you maybe have heard that terminology, morphology is the study of the shape of the earth. Okay, and that's what's going on. And what we're going to cover effectively in dealing with in this class isn't so much geology, but it is very much tied into geology. But what we're looking at, though, is what are the resulting landforms that we see on the surface of the earth? And there's a variety of different forces that are actually working on the surface of the earth that are coming in from both the tectonic forces are coming in and are being generated by processes that are going on underneath the surface of the earth. And then there are things that are going on the surface of the earth that begin to break those rocks down, the weathering processes. So we've got the forces that push, move, and raise the Earth's surface. Those are generally going to be called tectonic forces. And then we have the forces that scour, wash, and wear down, weathering processes. So we have these two types of processes going on that generate the surface that we all live on. So what's going on? Well, we have these rocks, okay, that are making up the crust of the Earth. And we've got three main types: igneous, sedimentary, and metamorphic. If you take geology, you'll get into what all those different types of rocks are. Suffice it to say, the short summary is igneous rocks are those rocks that are coming up out of the surface or from below the surface of the earth that are coming in as molten rock. And it's either molten material that has been extruded onto the surface of the earth, and that's going to be certain types of rocks. And then there's going to be other types of igneous rock that's going to come up into cracks and fissures underneath the surface, and then that's going to cool. And we'll get into a little bit about how that actually plays out when we look at that stuff. We then have sedimentary rocks, which are made up precisely of sediments, sands, shales, clays, things like that. And then you have metamorphic rocks. And metamorphic rocks are transformations of igneous or sedimentary rocks that under intense heat or pressure below the surface of the earth are transformed. Their chemical makeup is transformed and they change. So they change shape. So that you can see that morph in there again. So we have a change in the shape of those rocks or the consistency of those rocks. They become something new. Here we have the Grand Canyon, and the Grand Canyon is a wonderful example of weathering processes when we get into that. So what we also see here are sedimentary layers, all those different bands. Those are all varieties of sediments that were built up over a long period of time. And then you have the surface of the earth, and then from this line kind of right up in there, which is the top surface, it wore away and we can't see it, but kind of right down through here in other photos, if you look at the Grand Canyon, you'll see it. You've got the Colorado and some of its tributaries flowing through this Grand Canyon, and those have done what? Scoured and weathered and worn away at that rock, at those sedimentary rocks, and are digging down deeper and deeper and deeper down through those sedimentary layers. Those sedimentary layers in turn get exposed, and now they're subject to being weathered away by rain and by wind and other forces that are going to begin to wear away and scrub away at that surface. Igneous rocks, as we mentioned, we have magma and we have lava. So magma is that rock that's below the ground that comes up into those cracks and cools off. And granite is a good example of that. Lava is the molten rock that comes out above the ground, out of a volcano or a crack or fissure in the surface of the earth, where the lava comes out and then it cools. Okay, and depending on the rate of cooling, you get different rock. So you might, if it cools in one way, you get basalt. If it cools in another way, you get pumice. And in another fashion, if it cools, you can get obsidian that comes out of there. So it's the type of material that's coming up in there. It's molten rock, okay, but how it cools is going to condition the type of igneous rock that you get. Sedimentary rocks, again, those are ones that are actually made up of this weathering process that's going on, that's taking all this other rock and that just weathers it down. It turns it into gravel, sand, silt, clay, all these different sediments that then get deposited, usually in some sort of water mechanism, but there are other types. So a stream bed and then flowing out into a larger body of water, and it will build up these layers of sediments over time. Over time, that pressure and the absence of water, that dries out and it turns into a rock. That rock in itself can turn around and be worn away into finer sediments. So you can have sedimentary rocks that transition from one type of sedimentary rock to another type of sedimentary rock. This just kind of gives you, again, here's a formation of limestone that's in there. There's a shale there as an example. Again, take a geology class and they will go into this in depth. I'm just going to scratch the surface on this. And we then have sedimentary rocks and igneous rocks that undertake some type of chemical reaction deep, usually under the ground, where they're subject to heat and pressure, and the mineral structure itself has changed. The chemical structure of the rock has changed. So it transitions from one type of rock to another. So shale becomes slate, or limestone, marble, granite becomes gneiss. Those are the different types of transformations that can exist. We then have the notion of geologic time, and the basic thing on here is this right here, this theory of continental drift. And this is the notion that Alfred Wegener had in the early 20th century, which is kind of one of those things that's sort of obvious. But now, once we were able to fill in those maps that we were starting to talk about, and we had a better idea of what the actual shapes of the continents themselves were, you can kind of look at those continents and see that if we kind of cut them apart or cut them out, they begin to start to fit together in a lot of ways, right? So South America and Africa look like they can fit together in different parts. And Wagner came up with this idea that, hey, maybe all these were actually part of one large supercontinent, or a couple of them that are there. And then it broke up and they drifted apart over many years. And that is the forerunner of what is going on with the notion of plate tectonics theory. And plate tectonics theory is the means that we have for undertaking some of these processes that are going to be generating some of the landforms that we see. So what are we dealing with? Well, there's this thing called the asthenosphere. This is this partially molten layer of rock that's sitting kind of right above the Earth's interior. You then have the lithosphere. And lith is just kind of like, if you've heard the term monolith, right? A monolith is a single standing stone. So lith, right, is a stone or a rock. It's the rocky crust that's on the outermost layer of the Earth. And you've got a variety of things. That's the continental land masses, and it's the land mass and the set of rocks that are underneath the oceans, okay? So you've got these different sets of rocks that are out there, because it's not all one uniform piece, right? The continents are different pieces of rock. What's below the oceans, that's another segment of these rocks, and these are called plates. And there's about 12 big ones, and then several smaller ones that kind of fit in over the surface of the Earth, almost like kind of fitting together puzzle pieces, although it's not quite so neat. But you have these giant plates that then sit over the surface and basically are floating on top of this asthenosphere. This kind of just gives you the graphic of what we're looking at here. Here's our ocean crust here. Here's our continental crust. And then as it kind of sits there, it sits over and above this mantle in the asthenosphere, and effectively the continents and the oceans, they're floating on this molten mass. And the idea is that we have convection going on. So if you're familiar with convection, that's the truism or the observation that, warm air rises, cold air falls. But it's this notion that what is warm or hot rises and what is cool begins to sink. And as we're dealing with that stuff, right, that creates convection, these circular flows and patterns that are going on. And so that movement of that magma up and down, right, rising and falling, is going to generate the movement of the plates. And that movement of the plates then creates certain features or activity that's going to generate features. So here, this is just giving you some of the different plates that we can see, and there's a couple other maps that are out there as well that are in the textbook that you can take a look at. But these are some of the larger plates that are out there. So you can see up here, here's the North American plate, and somewhere over here we join up with the Eurasian plate. Below that is the African plate. You then have the Indo-Australian plate, which is really interesting. So if you notice, this plate has Australia, which is its own continent, but then also part of that is India. Sometimes you'll hear India referred to as a subcontinent because it is coming off of this plate. It's not part of the Eurasian plate, but it is pushing off of this Indo-Australian plate, and it's actually ramming into the Eurasian plate. And that force of it impacting the Eurasian plate, as you'll notice right through here, it's the Himalayas. Okay, so those mountains are created essentially by folding up the Indian continent, slamming into Eurasia and folding up part of that Eurasian plate, and you're generating mountains as a result. We also see here the Philippine plate, and we have this little Nazca plate off of the coast here, a couple of smaller plates through the Caribbean and along Central America, and the South American plate, and a variety of these other plates that kind of fill in the different boundaries along those plates. And it's the boundaries of these plates that are where there is a lot of interesting activity going on geologically that then has a landform impact over time. So you can see the San Andreas Fault, these different types of boundaries. You'll notice where the San Andreas Fault is right through here is at the boundary of the North American plate and this Pacific plate that's here. Moreover, you go work your way up the coast and across down through Alaska, down over to eastern Russia, and then down through the Philippines and Japan, and you come down and then into the boundaries through lower Southeast Asia, and then the Papua New Guinea area, and off over here into New Zealand and down the line there. What is going on here, and what we'll see in here in another graphic here shortly, is that is extraordinarily important for a lot of volcanic and earthquake activity, and it's associated with movement along these boundary points. This just gives you another idea of what's going on at the North Atlantic seafloor, and you've got these trenches and ridges that come up. So this is the Mid-Atlantic Ridge, which is sort of a mountain range. As these plates are running into each other, they kind of fold up and create little mountains that come about. And these are ones where that has actually broken through the surface. These are sort of the Azores Islands. If you go and work your way further north, you'll get to Iceland. That's going on in there, that's on that boundary as well. And this is interesting, and this is going to get what we're going to be getting into here in just a second with these plate boundaries. So if we have this continental boundary, like right here, and then we've got another plate boundary that's coming in, those plates are running into each other, they're bumping in, and one is riding up over the top and pushing the other one down. And as it does so, it can push magma up through some of the cracks and fissures that are existing there, and essentially push this magma out through the surface, i.e. through a volcano. And so you get these mountain ranges from that folding, but also volcanic mountain ranges that might emerge as well as you get into these subduction zones where these continental plates are bumping into each other. And this really begins to bring it home, hopefully. This is, again, the Pacific plate. Here's the North American plate, the Eurasian plate, here's that little Philippine plate. And you can actually, and here's that Indo-Australian plate right through here. You can actually see along these different plates, this is that Nazca plate that's right off the coast of South America, and a couple of the smaller ones are right through here. All of those little red dots that are on there are earthquakes. And everywhere you see a black cone, that is a volcano. And if you'll notice, right, along the boundary of all of these plate zones, there are a variety of different earthquakes that are going on. That's where the earthquake activity is generally most highly concentrated, and as well as most of the volcanoes. In fact, most of the active volcanoes are going to be along these boundary zones and these various subduction zones that are going to exist. So if you work your way into the United States, if any of you have been out west and you go into Northern California, there's a large mountain that dominates Northern California, and this is up in that area around, the wonderfully named California town of Weed, amongst others. But working your way toward the Oregon border, and there is Mount Shasta. And Mount Shasta is a huge mountain. It's got sort of that classic volcano shape to it, and it is actually still technically an active volcano. And you begin to work your way up through the Cascade Range, right through that, up the coast, and you get there, and then you get to Mount Jefferson and Mount Hood, which is right outside Portland, and you start working your way, and there's a whole series of mountains, and you get to Mount Rainier, which is just outside Seattle, and you keep working your way around, up around through there. One of the things that's really interesting is that one of the big mountains that was between Mount Hood and Mount Rainier was Mount St. Helens, or still is Mount St. Helens. And if you're, of age, you'll remember when that exploded. It had a massive explosion, a massive volcanic explosion that basically lifted off the top third of that mountain uh, and devastated a huge area in kind of southwest central Washington state. It could have been extraordinarily devastating and deadly if that volcanic activity had not gone on at St. Helens and instead had happened at Mount Hood or Mount Rainier. But it still potentially could. Mount Rainier and Mount Hood are still active volcanoes. You work your way up through here, you get up into Mount McKinley. It's the tallest mountain in the United States. It's one of the volcanic islands. And you work your way all along that whole island chain in Alaska and come over to Russia. And then you work your way down right through here. And here's Japan. And one of the things that happened to Japan a couple years ago was the giant tsunami. Well, the tsunami is an earthquake event. It's an earthquake event that's happening underneath the ocean, excuse me, as then pushing water outward as that happens. Just think of like if you fill your bathtub up with some water and you take your arm in one end of the tub and you just kind of push that water, and how it just moves that entire water and it sloshes up and kind of just, generates a big volume of water at the other end of the tub. That's essentially what's going on with a tsunami. It's a big slip and a push, and it generates a huge amount of volume of water movement that's displaced, and it rushes in towards shore. And as you can see, if you look at videos on YouTube, etc., that show that it can be extraordinarily devastating. Again, what's the big mountain in Japan? Fuji. Well, guess what? Fuji is an active volcano. And you work your way down through here, down through the Philippine Islands. There's Mount Pinatubo and some of the other places that are there that have had eruptions. And back off over here along this boundary right through here. This is where the large tsunami occurred back in, about 15 years ago, that in Banda Aceh and some places like this in Indonesia and down through Malaysia, that generated a massive amount of devastation there. And it works its way back out along this chain and down through New Zealand. So Auckland had some major earthquakes a few years ago that were going on. Over here again on this side, you work your way down where there have been actually some active volcanoes working along the Andes Mountain, the southern Andes mountain ranges down along in Chile, and also some very massive earthquakes going on down there on occasion as well. And we can see other locations where this is happening. Iceland is right up here, and it's got a couple active volcano that are going off on occasion. Sometimes actually when there is air travel between North America and Europe, depending on the flight path that they may have to make alterations if these Icelandic volcanoes are active, because it will send up a lot of ash that can interfere with aircraft engines and things like that. And again, here we have that trapped surface of the earth and the pushing up, the uplift that's going on. And we also have this, where we have those continental masses pushing in. So this is going on in India, okay, where you've got that folding that's going on, that's creating essentially the Himalayas that are going in there. But when you also have those subduction zones, these things back here, you can have on these surfaces here, this pushing down of the surface. And for us, we can actually see that here. So if you look at this here, this is essentially the landscape that we have in eastern Tennessee. We are part of this ridge and valley region of the eastern part of the United States, right? Think about ridge, valley, ridge, valley, ridge, valley. It's what we kind of live and drive through every day. When you move east, so if you've gone over to Asheville and then started to work your way down toward, say, Charleston along the coast, you'll get out there and you'll come down, and it's almost like literally the earth just sort of begins to just curve down, and you are really beginning, and you can sort of really recognize that you are going downhill. You are heading toward the coast, and we see that in our area, things that you can see quite easily. Again, here's the ridge and valley section. This is actually the Pennsylvanian part of the Appalachian mountain range, which is part of what is running right through here in East Tennessee. And you see these varieties of different ridges and valleys that come about. And what we also see in this region are weathering effects. And so you see the ground level, and then as it's worn away, you get sort of an idea of what that actually looks like also within those layers when you drive over to Asheville and you look at some of where they've cut the freeway through there, and you can actually look at some of the stuff that's going on in the rock layers that are going on there. Faulting, as we're dealing with these plate boundaries and other geologic effects are going on below the surface, you're going to create different cracks and breaks in the rock that are going to basically push stuff up or push stuff down, and rifts and things that are going to pull things apart. And you see that. So you get escarpments that come about. Some fairly tall escarpments might exist. There are quite a few out in Texas. If you are anywhere in the area west of Austin, San Antonio, heading out towards San Angelo, Texas, out in there, you're going to come across something that's called the Llano Estacado. And the Llano Estacado is an escarpment. It's a huge landscape feature kind of in west central Texas that kind of breaks the high plains kind of the Panhandle area from the hill country and central plains of Texas that are out in there. One of the other features where you're really going to see a rift valley is not here in the United States. It's actually over in Africa, and it is in the area around Eastern Africa on the Horn of Africa. So think Somalia, Ethiopia, down toward Tanzania, and it's called the Great Rift Valley. And so it is a portion of where Eastern Africa is starting to effectively calve off or split off of the main African continent. That's down in there. So diastrophism, just to back up, diastrophism, those are the push and pull forces that are going on, right, that are mostly going to be associated with earthquakes, but also just those uplift processes, folding processes that exist. So the primary tectonic forces are diastrophism and volcanism. Okay, just wanted to make sure we got that out of the way. So we got diastrophism, where we got a lot of earthquake activity that's going on. Most earthquakes are extraordinarily mild, and we don't really even feel them. They just happen and occur all the time. But on occasion, they get to be very massive and can have a huge and devastating impact. I mean, your book cites this one in China, yet almost about 250,000 people were killed. But you've got to say that there have been some other massive earthquakes, Haiti, for example, other places like that, which hundreds of thousands of people are killed as a result. Another thing here, here's the tsunami like I was talking about. So you've got this little break that happens below the surface, and it pushes that water up, folds that water up, and that wave is just extraordinarily devastating because it can be 50 feet or more of that water that moves in, and it can move very, very quickly. And so that's a huge volume of water. So there's a lot of force behind it. So it can be extraordinarily destructive when those things hit. Volcanoes that are going on. Again, most of these are going to be happening at or near your plate boundaries. You have the stratovolcanoes, that's your classic volcano shape, and shield volcanoes, which are usually sort of those cracks and fissures where lava flows out from the surface that goes on in there. So here we have our stratovolcano on the left, and then a little bit kind of a shield volcano there, crack fissure type on the right. One of the other things that we do see where we have are these hot spots. These are little cracks or openings in the continental crust that allow magma to flow up as as I mentioned, a little mantle plume that comes out, and that goes up, builds up these mountain ranges, and those will eventually breach the surface, and an island will form. And then over time, those islands are eroded away. So this is what's going on with Hawaii, where there are currently an active, if you remember, we had some lava flows, major lava flows in the last couple years on the Big Island that created quite a bit of devastation. And that adds in there. There's another plume that's coming off. So there's a new island that's going to be forming, Lohi or Loihi. I'm not quite sure how that's pronounced. But you can see here's the older islands, and they've been eroding away down into the sea. There are actually subsurface islands or mountains that are back off over this way that used to be above the surface but have eroded away because of the wave action that's going on. Magma may not reach the surface, so you can get these granite formations that can come about. So Stone Mountain would be down near Atlanta would be one of the closest ones for us that we would be able to go ahead and see. That's up in there. Then we have gradational processes. Gradational processes, weathering, mass movement, and erosion. Most of this is going to focus on weathering and what's going on there. So we have mechanical weathering, which is one time, and it's basically how is the rock being broken down and decomposed? What's going on? We have some type of atmospheric factor usually that's going to be in play: water, air, and temperature. And the other thing that's important with respect to weathering, it's not an all or nothing thing, right? There's a variety of these different processes that all can kind of combine to wear that stuff away. So chemical weathering is going to be chemical processes. Mechanical weathering is just going to be the physical disintegration of earth materials. So root action, right? So if you've seen trees and bushes on the side, and in rocks on the sides of the road, that's going to be root action. Those roots are going to get in there, break that rock apart, crack it. Once it's kind of cracked and open, salt crystals can get in there. You can get ice and snow in there, and water will get in there, and that frost or snow that'll expand and contract, and that will also begin to break the rock apart, and those rocks can then fall. And then as those rocks are falling, they'll break apart, they'll knock into other rocks, chip pieces off, etc., and it will slowly start to crumble and crack the surface. In addition to that, you can have minerals and that are in the rocks themselves that are then going to undertake some type of chemical reaction. If you have irons or coppers or some other types of metals, you are going to have potential for a rust to form. And if you've ever seen an old rusted out car and you go up there and touch it, when it's really rusted through, it essentially will just turn into powder. And that same sort of thing can happen in the rock, is that iron or whatever that's in there, it will oxidize, it'll effectively sort of turn into powder. As that's doing, it's leaving the surface, so the surface is wearing away. But then that's also going to allow those cracks and fissures to form for some of that other mechanical type of weathering processes to take place. But also water in and of itself might undertake a chemical reaction. You might have carbonation. If you have different types of material that are in there, they're going to weather away and get some type of carbon dioxide gas or something that's in there, and you get carbonic acid, and then that will actually sort of scrub away the surface of the earth a little bit. And as these weathering processes are occurring, right, that rock is becoming and decomposing into smaller and smaller pieces. That becomes the basis for soil. Now, technically, soil is not just the dirt, okay? It's not just the rock. You can really offend the soil guys down at the university by just calling it dirt. Dirt's just essentially sort of the inert matter. Soil itself also includes the organic matter that's mixed in. So it's a broader thing than just the decomposed rock. So just want you to be aware of that. But you have to have that decomposed rock and that material to actually begin to get the soil that that's going to come out. Mass wasting or mass movement that's going to be in there. This is usually when you get, say, for example, around here where you have some of the hillsides and slopes. This is where you get a lot of groundwater and sort of super saturated soil. And what happens when you get super saturated soil, it turns sort of muddy. And what does that mud do in super soft soil? When it is subject to gravity, it begins to move, it begins to slide. So you get mudslides and this soil creep, the landslides, etc. It can lead to avalanches and things like this. But if you notice here in this photo, those trees normally, right, should be growing straight up, but because there's been, say, some type of super saturation in that soil, it's started to slowly, right, flow downhill. And so the trees are just moving with the land mass that's there. The talus, this is that bottom stuff. It's that cone of rock that's at the bottom of the hills and mountains. So if you want to see that, it's got a great photo back up here at the beginning. Okay, so you look at here, we've got these long spires of what's left of what's been eroded away. But all this down here, all these this little cone shape of rock and layer that's down there, that's the talus. And you can see along there, it's this little bit of all these formations that are in the background there. That's the talus. And we'll get back, we'll find the right one here. There we go. So we have that. One of the other things we see is water, okay? Water movement is huge. And the faster the water is moving, the more erosion is going to take place. So fast moving water is going to erode more than slower moving water. And we have different issues with that as well. Running water is the most powerful, or one of the most powerful erosional agents that are out there. And it's essentially, it's just wearing stuff away. But also, if you look at that, water is going to be picking up sediments. It's also going to be picking up trees and other debris. And all that stuff is actually going to act as like giant abrasive surface, kind of like sandpaper or like a a sandblaster that has, that with the water in it that actually then goes in and it scours out the surface as that water's moving through. And we call all the material that's in there the load. And so high velocity, high load is going to generate a lot more erosion potentially that's in there. As the water flow slows down, more stuff becomes deposited, right? So the heaviest stuff deposits out first, and the lightest stuff keeps getting borne along down as the water slows down. So you get this deposition environment of this fine sedimentary material that can build up. That is usually highly desirable, right? That's the bottom land, okay, that you may have heard about. It's extraordinarily fertile, usually agricultural land, because of those rich depositions that come over. So the Nile River in Egypt was historically and has historically been driven by this deposition of material coming down from the African highlands. And so as it comes in, it creates these new deposits, and those new deposits refresh and replenish the soil and allows for greater amounts of agricultural fertility to be there. So it's an extraordinarily important process. You do have this. You have a lot of flooding that could potentially, so this is New Orleans again after Hurricane Katrina. We'll talk a little bit more about hurricanes for chapter 4. But those hurricanes can also then lead to flooding and then the redeposition of material as a result. A variety of different landscapes that are a result. So if you're in a wetter or more humid area, you'll get certain types of landfalls or certain types of landscapes and certain sort of landscape agents versus arid areas. So in humid areas, us, okay? So think of East Tennessee. What do we have? We have a lot of waterfalls, these channels. We have some occasional rapids, think the Hiwassee, the Ocoee, things like that. We also have the floodplains, and we have meanders. That's where the streams just kind of wander around, right? They're not traveling straight. They have a meander to them, which means they kind of that back and forth movement. Because of the deposition, you get a lot of natural levees. So we see this in the Tennessee system, the Ohio River system, the Missouri, and especially everything that's pretty much attached to the entire Mississippi drainage basin that's out in there. When you move out west or into drier areas that are around there, but within the United States, you have not as much vegetation. So you're dealing with more arid, sparser vegetation. So there's not a whole lot holding back or slowing down that water. So the water can actually move very, very fast. And you get a lot of these playas or alluvial fans, but that's also where you get those really dramatic buttes and plateaus, mesas, the arroyos that you see, like we saw in that lead-in slide for the chapter, as kind of a typical arid environment and what we expect to kind of see. So this is a meander here, okay? So this stream through here, that's a meander. This right here is a part of where the river used to flow and has now been cut off by subsequent deposition of material. This is an oxbow lake, okay? And then here you have some additional stuff where you have these braided streams that come out. So you have this deposition that's coming down out of the mountains. All this material here is the alluvial fan. And then as the water flow gets down to the bottom, it starts to break up into these smaller streams and then works its way down, and the material is deposited in a variety of different ways. We then have groundwater. We don't really need to worry about that. The important thing about groundwater is that as that rain and water is coming in, it's soaking into the surface of the earth. That's good. And one of the things that's going to be extraordinarily important for what we're going to talk about when we get to agriculture and some of the human impacts are these aquifers. And aquifers are these large sort of porous underground geologic structures. They're very large, very extensive, and basically when the groundwater soaks in, these are kind of like, you can think of, they're the underground storage tanks for all that rainwater and that's coming in. So it's extraordinarily important, primarily for agriculture, that comes in there. So one of the things that we do also see is the potential as the groundwater gets in and soaks down, if it comes into contact with certain things like, again, some chemical weathering can actually take place, where you get in to limestone formations or other types of formations where that water is then going to dissolve that material. And so you get caves, underground caves, or sinkholes, things like this. Those types of features that are going to come about. So you get a lot of this. One of the things that is the more dramatic representation of this is called karst topography, where you get these limestone areas that are in there with a lot of different sinkholes that will form. So there's a lot of that in East Central Florida that you can go see, but also as you work your way up through here, up towards, say, Mammoth Cave up in Kentucky, and some of the other big caves that are down through up in Virginia, heading up through Western Virginia, but also through our area here, you can see a lot of these. Another place that you can go see some of these things actually really dramatic are in the Yucatan Peninsula down in Mexico, where they have the cenotes, and which are kind of these sinkholes and the underground caverns that then have the water that's filled up in there, or underground streams that have been running in through those. And it's really, really interesting topography to go take a look at. Glaciers are huge. They're not as much of a landscape effect right now, primarily because most of our glaciers are actually in retreat. I'll clue you in on a little bit. We've been coming out of an ice age for about the last 10,000 years. So yes, the Earth is warming up, because we were coming out of an ice age. So that's kind of what the end of an ice age means, is you're warming. So what does that mean with respect to glaciers? It means that those glaciers are probably going to begin to retreat. What are some of the big ones? Greenland, Baffin Island up in Canada, Antarctica. There's also some fairly large ones in the Altai region in in eastern Russia that are out there. So roughly about 10% of the Earth's surface is under ice. The biggest issue is that back with the Ice Age, and at the end of the Ice Age, there were these periodic movements, where the glaciers would advance and then they would retreat. And it's that advancement of a glacier and the retreat of those glaciers that creates a lot of landform features that we see here in North America that really had an effect on the area around the Great Lakes, Minnesota, and up into the Pacific Northwest in places, and a lot of different places within sort of the northern part of the United States and into southern Canada as the glaciers advanced and retreated. And so you push a lot of rock and pebbles and silt. And for glaciers, when they're pushing it, it's called till. Till, it's kind of related to that talus, which is all the debris that's at the bottom. So till and talus. And then when we get into mining and people pull stuff up out of the ground and they deposit it into big piles, it's tailings. So talus, till, tailings. It's kind of all the detritus, all the junk that's left over that's pushed around out there. And this is just a couple things about what those look like when you get into those features. The glaciers come down, and basically they're really scraping and carving away the surface, and they create these really jagged mountain peaks and systems. And so that's usually an indicator of glacier activity. But you get these those troughs, as it called, and then you get the horns and the cirques, the arites, as it's all kind of carving out all the different things. Don't worry too much about the terminology here. Just kind of recognize what's going on with glacier processes. And this is kind of where we also see where the glacier's pushing out, and we get these little ridges that come about and that are coming these moraine. They're called moraines, and they're called sort of like the terminal moraine. That's effectively the last moraine that you got to, is kind of where the glacier pushed out finally ended. But you got these recessional moraines as it's kind of pulling back and stuff drops off. And these glaciers, what's going on here is under that, the glaciers are massive sheets of snow, right? And then as it gets more and more pressure and more snow laid on top of it, it's going to turn into ice. And that ice is then going to move. And it's very, very heavy, obviously, because it's ice. And you can kind of think about, well, how does that snow sort of really turn into ice? Think about when it has on occasion snowed here, and you may have driven over that snow and kind of pressed that down and compacted that, and how it's snow, but then later on it kind of turns into a nice sheet of ice. Think about that happening year over year over year for hundreds and thousands of years, and it builds up time and time again. And pretty soon you get some very, very thick sheets of ice. And then below that, under all that pressure, that bottom layer kind of turns into sort of a toothpastey type consistency. And that is going along and it's picking up rocks and trees and whatever else is out there. And that's just scouring the surface. And because it's not uniformly smooth underneath there, it's also then leaving a lot of these different little features. And as it's progressing and moving forward and backward, it's depositing this material, but it's also carving stuff out. And it'll drop out these little kettles and little hills that come in there. And so you get kames and drumlins and then little kettle lakes and stuff like that that remain. Minnesota, for example, what's the nickname for the state of Minnesota? The land of 10,000 lakes. Well, where do those 10,000 lakes come from? A lot of those are these little kettle lakes that were formed by these glaciation processes over time. Waves and cliffs, right? So we got waves and currents, I should say, and coastal landforms. This is just that wave action that's going to scrub away and just wear away at the coastal surfaces. And it's going to deposit material, sands and stuff like that. It's also going to take it away, but it's going to erode away the surface that's going on out there as well. So you can see these waves, they come in a circular pattern, and it begins to wear away at that surface, and then it's also creating deposition environments for that sand over time. And a variety of different features can form as a result: beaches, sandbars, etc. A lot of which have to do with, you've got this depositional environment that's, say, coming from a river that's coming out depositing material that builds up on a beach. There is wave action that's bringing the sand in, but as that is coming out, you'll see we have this current that's out there. That material is flowing out this way, and it gets caught onto that current, and it starts to build up, and you get a little offshore sandbar. Or it begins to sort of just push away a long part of the beach there, and you get this thing which is called a spit, and that can actually come down and become longer, and then it can eventually potentially curve back in and create a little backwater lagoon along there. So you've got a variety of different features that might result from those currents. Coral reefs we see out in the Pacific. We've got the Great Barrier Reef, primarily they're coral reefs, but you get this coral organisms in shallow water. Barrier Reef off the coast of Florida, off the coast of Belize, and then the big one down there in Australia. But you also see these manifesting themselves a little bit in atolls that come about out in the South Pacific, where you get these volcanic activity, and sometimes there'll be some coral that'll pull in around there, but they're fairly small reefs and that are formed that are usually surrounded by some fairly shallow water, and these are not very high above sea level. And we see a lot of these atolls that are out there. These were highly important during World War II. So if you take a history class covering World War II, and you're looking at the war in the Pacific, a lot of the major battles that were going on in the Pacific during World War II were for the control of some of these little atolls, because they're fairly flat, and you could actually, put an airstrip on those, and then position your bombers or transport aircraft, etc., around those, and then bring the Japanese mainland a little bit nearer for doing the bombing and everything like that needed to happen. So we were trying to control these atolls or deny their control to the Japanese during World War II. Wind is a huge depositional and erosional agent that's out there. Creates a variety of different landforms. You've got a lot of different things that happen because of the abrasive action. When that wind picks up sand or other particulate matter, it's like a sandblaster again. And so it will begin to wear stuff away. That happens. And so you see dunes, right? That's sand or other depositional material, and it's carried by the wind, and it creates these landscape features that we see here. One of the things that we see in the United States that's extremely important for agriculture is that you get these wind-blown silt deposits that build up over time. And this soil is called loess. Okay, so it's L-O-E-S-S. It's not loess or los, it's loess. That is how it's pronounced. But you see it in these westerly wind belts, and you find it in the US, Central Europe, Central Asia, a little bit in Argentina as well, and up in China. And up in the Pacific Northwest in eastern Washington and western panhandle of Idaho is an area of the country called the Palouse. And the Palouse is largely made up of the wind-blown silt deposits. And those depths of soil can be 100 to 150 feet. And it's extraordinarily rich, productive soil. And so it's a huge agricultural zone up in there, primarily growing things like wheat and peas and lentils and some other stuff like that. A lot of this loess soil here in the United States is highly concentrated around Iowa, Illinois, Missouri, in through there. And that is essentially sort of the corn belt of the United States, where we have these very, very thick layers of loess soil that are very, very productive agricultural production regions, excuse me. And once we get that into, and that kind of leads us into the last little bit here, once we get all these landforms, what can we do? We can actually begin to describe regions. So, do we have a landform? Is it dominated by mountains? Is it coastal? Is it a plain? Is it a plateau? What's going on with it? We can actually look at what's the dominant landform region or the dominant landform generating process, and we can begin to build up regions. We can begin to do this even more, as we'll see with climate, when we start adding not only the landform to it, but we start adding the climate and weather features of a particular region. And then that's going to, in combination, that's oftentimes going to also characterize the types of plants and animals that are going to be found there. And we get these complete landscape regions that emerge. And I'll touch on that a little bit more on the next video. So thanks, guys.